Now moving on to some energy, or to the concept of energy. We really care about energy in physics, and it's measured in joules. So all objects in motion have energy, have kinetic energy. Now, before we jump into that, it's sort of tricky to define what energy is because it's sort of a round and round definition. Because quite often we say that energy is the ability to do work, and then when we try to explain work, we say work is the transfer of energy. So energy is a bit complicated in that sense to define, but I think the best way to look at it is through work. Work is when you apply a force over a certain distance. That's work, and that's the transfer of energy, right? So we need energy in order to do stuff, right? In order to apply forces, in order to make things move, in order to apply forces over distances, and so on and whatnot, and so on. So all objects in motion have kinetic energy, and you probably would have heard of that in high school physics or even before that. So you've got half mv squared. That's going to be the kinetic energy of the object. So m is the mass, v is the velocity. So anything with velocity has kinetic energy. The position of objects can also give them potential energy. So you can have gravitational potential energy, or you can have elastic potential energy. The formula for which is out of syllabus, but you still need to understand the concept. Collectively, we call all these mechanical energy. So kinetic energy and different forms of potential energy, particularly gravitational and elastic. So gravitational potential energy talks about when an object some height above the ground, so let's just say h meters above the ground, it's got some gravitational potential energy. What that means is some amount of energy had to be put in order to put it at that position. So we've sort of stored energy, right? And then if we let go, then it actually converts into other forms of energy. So kinetic energy, for example. Another example is if we have a spring, right? And we compress that spring this way, right? We're storing energy, and then if we let go, that potential energy is converted into kinetic energy. So collectively, these are called mechanical energy. All these together is called mechanical energy. And if we consider systems without friction, there is no way to remove energy from a system of objects. This is called the conservation of mechanical energy. So if we ignore friction, right, there's no way to lose energy from these systems. You conserve energy all the time. The total energy initially has to be equal to the total energy finally. And that's sort of very related to the law of conservation of energy. So because of the conservation of energy, we cannot destroy it, and the only thing we cannot destroy or create it, right? The only thing we can do is transfer it between different forms. So when you drop a ball, as it falls, it converts potential energy into kinetic energy, causing it to speed up. So let's just say you do some work on a ball, so you're applying a force over a distance, and now that ball has potential energy, right? And once it has potential energy, you drop it or you let go, then it starts speeding up. It's transferring or turning that potential energy into kinetic energy. When friction slows an object down, it actually converts kinetic energy into heat and sound, and sometimes light. Now, what I mean by that is the law of conservation of energy is still perfectly fine when we talk about friction, right? It's not that the law of conservation of energy breaks down because of friction. It's just that it's harder to keep track of the energy, right? Because it's harder to find, how much air are we heating up, or how much energy is lost when we bounce a ball on the ground or something. That's a bit more tricky to keep track of, although it's still possible, right? So when friction slows an object down, it converts its kinetic energy into heat and sound, and so it's not. So we can't say mechanical energy is perfectly conserved. Here's an example. How are we going for time? Okay, yeah. So maybe we can do this example quite quickly. We've got a 60-kilogram physics teacher, and he's pushed off a 70-meter cliff by a disgruntled student, unfortunately. What is the teacher's gravitational potential energy? So initially, the teacher's out on the cliff, right? Teacher's on the cliff, and he's got a gravitational potential energy because he's at some distance above the ground, so 70 meters above the ground, right? And so, what is the gravitational potential energy of the teacher? Well, we saw the formula before. It's U equals mgh. It's dependent on the mass of the teacher, the acceleration due to gravity, and the height. And that formula is actually not too hard to derive. It's pretty much directly related to the work required to get the teacher up there. So U equals mgh. M is 60 kilograms. G is the acceleration due to gravity. And h is the height above the ground, so 70 meters. So we can say that the teacher has 60 times 9.8 times 70, which is 41,160 joules as a unit of energy, joules of potential energy. Now, part B is where it gets interesting. Once he gets thrown off the cliff, right, the question is how fast will the teacher hit the ground, ignoring air resistance? So if we don't lose any energy to all these other forms of, or all these other forms, how do we find how fast he's going? So in order to do that, we look at what the total energy is initially. So remember, energy initial equals to energy final if we don't lose energy to all these other things. So mechanical energy is conserved. Initially, the energy is in the form of gravitational potential energy. There's no kinetic energy. Once the teacher hits the ground, or like is pretty much touching the ground, or his feet or the center of mass is very close to the ground, he's got pretty much zero gravitational potential energy and all kinetic energy. So we've got this equation here, and we're interested in how fast the teacher will hit the ground. So we're interested in the velocity. So what we can do is we can cancel the masses. We can pull the 2 over, so we get v squared equals 2gh, and we can square root both sides. So we get v equals square root 2gh. So we've got this equation here, from into which we can sub in our numbers. V equals square root 2 times 9.8 times the height, which is 70 meters. So we can say square root 2 times 9.8 times 70. So that's going to be approximately 37.04 meters per second. And so we're done. That's how fast the teacher will hit the ground. Now, that's more related to speed. If I ask for direction, he's going downwards, obviously. But 37.04 meters per second is how fast the individual is going. So yeah, that's how you deal with these sort of questions. Now, how does this relate to forces? Well, the force applied to an object accelerates it, thus increasing its kinetic energy, and that's called work. So again, work is the ability. Energy is the ability to do work, and work is the transfer of energy. So the work done results in an increase in kinetic energy, and it's the dot product. Now, dot product here is a specific terminology when it comes to vectors, but for now, it's okay to notice that. It's okay to say that we're interested in the force. So if we move an object from here to maybe here, right? Travel displacement of s. We're interested in the component of the force. This was theta. We're interested in the component of the force that's in the direction of motion. So that's only this horizontal component here. We're not interested in the vertical component, we're only interested in the horizontal component, and that's where W equals Fs cos theta comes from. So we have our block, and we have a force angled, and we have some point later, the block's traveled some displacement forwards S. This angle in here is theta. Only the F cos theta component, that's the horizontal component. If you use trig, you'll be able to see that only this component, this horizontal component, actually does work, because the downwards pushing component doesn't actually help in moving the object over to the right. It just pushes it down into the ground. So it doesn't really do anything in terms of work. So we can say F cos theta, so the component of the force, times the distance that it travels is equal to the work done by that force. So we say that the force does work of Fs cos theta. So force times displacement, or the component of the force in the direction of displacement, times the displacement. So the dot product is pretty much very related to this. We're looking at how much of the force is in the direction of displacement, and then we multiply those two together. Because remember, displacement and forces are vectors, and we want a way of multiplying the vectors together, taking into account how close they are in direction. So that's where this dot product concept comes from. And if you do extension 1 mathematics in year 12, you'll be able to see more on that. But just know that we're interested in the component of the force in the direction of motion times the displacement as it travels. How are we doing for time? I think we can do this one. So we have a 0.5 kilogram cannonball, which leaves a 1 meter long barrel traveling at 100 meters per second. And we're interested in how much force was applied to the cannonball over the length of the barrel. So we can assume that this force is uniform, because if it's not uniform, it gets a bit trickier. But if we do assume it's uniform, we have this force that's pushing the cannonball, as long as it's in the barrel, it's pushing that cannonball through the barrel, speeding it up and up and up, until when it exits, it's got 100 meters per second velocity. So when you think about the law of conservation of energy, right, the work that's input by that force turns into kinetic energy at the end. So let's figure out what the kinetic energy is in. Let me state this first. So the work that's done by the force is equal, okay, maybe I'll use a different subscript because that looks like work final. Work that's done by the force is equal, or the force due to the cannon, so work C, is equal to the kinetic energy final of that bowling ball, right? Or sorry, of that cannonball. So the work done is completely transferred into forming kinetic energy. So all the energy that's input is turned into kinetic energy. So let's figure out what the kinetic energy final is. That's not too hard to do because we have all the components necessary. Kinetic energy final is half mv squared just by the formula of the kinetic energy. So we got half times the mass. Mass is 0.5 kilograms, and the velocity is 100 meters per second. So 100 squared. So putting that into the calculator, it's 0.5 times 0.5 times 100 squared. Yeah, okay, and that's 2,500 joules. That's the amount of energy that the force due to the cannon does. Right, the cannon, within the cannon, the cannonball experiences a force, and that force, that force causes a kinetic energy. That force causes the object to speed up and up and up until it achieves a velocity of 100 meters per second, at which point it has a 2,500 joules of kinetic energy. It has a kinetic energy of 2,500 joules. So now we're interested in the force, right? And we said that the work done due to the cannon is equal to Fs cos theta. Let's assume that the ball looks something like this, and the force is in the same direction as the barrel, right? So the angle between the force and the displacement vectors the force and displacement vectors are parallel, so the angle between them is 0. So that's just going to be Fs. So, and again, the length of the barrel here is equal to, so we're looking at the work on cannonball, right? Fs equals 0, and then that's going to be F times S. F, we're trying to figure out. It's the uniform force that we're trying to figure out. S is the distance within the barrel, and the barrel is 1 meter long, so we can say F times 1, so just F. So we've concluded that F equals to, or even before I jump to that conclusion, because WC equals to the kinetic energy final, we've concluded that WC equals F in magnitude, and so the F equals to the kinetic energy that we found before, so 2,500 newtons. So force of 2,500 newtons pushes that cannonball as it's moving through the barrel, resulting in it speeding up to 100 meters per second, at which point it has 2,500 joules of kinetic energy.